Hello, Haji. Good morning, sir. Shailendra ji. Good morning.
Yes, Dr. Krishan, am I audible?
Yes, yes. Good morning, sir. Shailendra ji. Good morning.
Uh, Hello.
Hello,
This is not you.
hello,
You are not audible to me, Dr. Krishna.
hello. Am I audible? Hello.
Jai Prabhu Jai Nandachiya.
Shailendra sir. Good morning. Hello. Dear all, kindly tell me, am I audible to you?
Yes, sir.
Hello.
Yes, sir. Yes, sir. Yes,
Yes,
sir.
sir. You are audible, sir.
Okay, 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 okay. Shailendra ji, am I audible to you?
Hello.
Dr.
Yes, yes,
Shailendra?
you're audible now. Am I audible?
Yes, your voice basically it is means quite slow.
Okay, let me use another lead.
Oh.
Is it better now?
Yes, yes, it is, I think, perfectly fine.
Okay.
So, sir, can we start now?
Yes, yes, yes. Yes, sir.
Okay. So, dear participants, very good morning to all of you. So, in this session, we have with us Professor Shailendra Kumar for the expert talk of this session. So, on behalf of Department of Computer Science and Engineering and the organizing team, I welcome you, sir, Shailendra sir. So before we start, I would like to introduce our expert of this session, Professor Shailendra Kumar. So Professor Shailendra Kumar completed his Bachelor of Engineering, Computer Science and Engineering in 2001, Master of Technology, Computer Science in 2005, and Doctorate of Philosophy in the Computer Science and Engineering from Maharshi Dayanand University, Haryana in 2017. He has more than 20 years of teaching experience at various esteemed engineering college like Delhi College of Engineering, Netaji Subhas Institute of Technology, NSIT, Ambedkar Institute of Advanced Communication Technologies and Research, etc. Currently, Dr. Shailendra is working as professor at Delhi Technological University, Delhi, India. He has published more than 80 research papers in various reputed international journal and conferences. So, sir, we welcome you in this session and thank you very much for giving us the time. So, sir, now you can start your session.
Thank you, Dr. Krishna, for this introduction.
Thank you very much, sir.
I'm pleased to be here with you to deliver a talk on information security today. Okay, so I'm sharing the screen with you. Is the slide visible?
Yes, sir. Yes, it is perfectly visible.
And it is moving also?
Yes, fine.
It is moving now?
Yes, it is moving.
Okay. Okay. Okay, so I'll be talking on information security today. So as we all are aware that almost in every organization, there is some confidential information. And in order to safeguard that confidential information, we are always in the need of a security system such that in the case that we have some outbound data to send to some outside world, in that case, we require that data to be encrypted so that it may be unreadable to the attackers. Then at the same time, we have some methods, cryptographic methods, which are embedded for the system within the organization also, so that the data may be shared means only to the authorized users of that data. So my topic for today's discussion will be some of the basics of information security. So I'll be talking about the various principles of security. Then we'll be talking about some of the different types of attacks, and followed by different cryptographic algorithms which are important for safeguarding the confidential information. So yes, so this is the introduction slide. So in this introduction slide, basically it talks about three important principles of security. So as most of you are aware of this also, if you are a computer science student or faculty. So we have the three principles as confidentiality, integrity, and availability. So these are considered to be the principles of security. So talking about confidentiality is basically that as we have a confidential information with us, we have a secret information with us. So we require some mechanism by which we will be safeguarding that information, confidential information. And the way out for safeguarding that information is there can be different means to safeguard that information basically. So there are different ways that we can apply the cryptographic algorithms and different types of cryptographic algorithms. So here the purpose here for achieving this principle is to safeguard the confidentiality of the data. The second principle, which is important in information security, is integrity. Basically, integrity as a principle, basically it is that it requires that the confidential information which is to be transferred from one node to other, it should not be modified during its transit. So that talks about integrity. So definitely that is an important pillar of the security system, integrity. And third is availability. So we have means with confidentiality and integrity, we are able to safeguard the confidential information against the attackers, and somehow we are also able to make the modification impossible if we are able to if we are able to ensure integrity of the data. But at the same time, what is important is whenever we are in need of that confidential information, that should be made available to the authorized user. So for that to happen, the third important principle of security comes up is availability. So as and when the data is being required, then data should be made available. And a very common, very simple example of that availability of data is whenever we go to an ATM and we require some information about your account, or you want to access your email account. So in that case, the data should be made available. So that is called as availability. And if the data is not available to the user, then definitely it will of no use to the system. So that is why we have kept availability also on the same level as we have kept confidentiality and integrity. Although it seems that availability is not that important, but definitely it is very important. So these are three principles of information security. Uh, Yes, this slide basically it talks about different types of attacks, which are definitely this is a very common slide, and you have seen it in number of literatures available in different books or in different journals on different tutorials. So you can see that the security attacks is classified into three categories here. So three categories are on the basis of the principles of security. That is one you have means the it talks about the attacks which are threat to the confidentiality. Then it talks about the second category, which is the threat to the integrity, and third one is which is the threat to the availability. So availability is quite simple to understand. So let's take it this first of all. So it is denial of service is the type of attack which is a threat to availability. So as we are aware that denial of service is whenever any client requests for any service from the server, in that case, it will be getting its services from the server. And if somehow some attack is applied upon to the network or to the server will not be able to provide its services to the clients. So that is possible because of this denial of service attack. And that's in this basically what happens is the attacker send out bogus requests to the server, and the server will be overloaded and will not be able to respond properly. So this is also considered to be very severe attack. So it means if the server is not providing service, then definitely it is, you can understand the severity here. So, and definitely if it's not able to provide its services, then definitely the data that we are asking for will not be available to us, and this is definitely a threat to availability. So in addition to that, we have then threat to confidentiality, and the two attacks which are listed. This slide might not be listing. There are some other attacks also, but it is considering few attacks in this slide we are considering. So one is snooping and traffic analysis, and snooping and traffic analysis is basically snooping is basically sensing, sniffing basically. So the server, the attacker or intruder basically will be having a continuous watch of the communication between the client and server, which are having a confidential communication of data. So so in that case, there are techniques by which the attacker will be having an information about the about the ciphertext. I think when all of you are well aware of ciphertext and plain text. Plain text is the data which basically we are having with us as a confidential information, which we need to share it with some authorized second user. So in that case, whenever we apply some cryptographic algorithm on that plain text, it becomes ciphertext. So whenever the data is in transit, it will always be in ciphertext, because the ciphertext is considered to be unreadable by the attackers. So, but in this case, snooping attack, the attacker will be having a sense of the ciphertext, and by using the statistical method, brute force attack, whatever it is, it will be guessing what the data is. So somehow the information related to the type of communication, type of data exchanged can be guessed by the attacker. Similarly, on similar basis, you have traffic analysis on the basis of the frequency of letters. It is the simplest of the attacks which is considered and which is taken care of also. But as a part of literature, we should be aware of this kind of attack, traffic analysis. So this is definitely in both cases, in snooping also and in the case of traffic analysis. Here the purpose of the attacker is not to modify the data, but here the purpose here of the attacker is to make use
Hello,
of
sir.
the
Hello.
Hello, sir. In a topic analysis, a packet modification is not done. I'm
Yes,
Gautam here.
yes,
I
Gautam,
asked
yes.
the I asked the question in topic analysis when we go with the Wireshark or any Nmap tool. I take an example here. The packet modification or packet crafting or packet poisoning is done, or it is directly attacker take the control on that topic.
I think this topic is not related to your question.
Okay, okay, sure. Thanks,
And
sir.
better, it is always better that we can take up the queries at the last rather than interrupting
Okay,
in
okay.
between, right? Okay. So this is about the threat to the confidentiality. Because in this case, we are safeguarding the confidential information. So this is threat to the system. So this is one thing. Then second is second, or basically the third type of attack which is possible will be the threat to the integrity, wherein we'll be looking for that the data should not be modified during transit. So we have various types of such attacks listed here in the slide. So we have modification, we have masquerading. Modification, simple modification of data, means when the attacker is able to have an access of the ciphertext and somehow has got information about the key or the encryption method, so it's really modifying the data. So definitely that is a modification of the data, and it is threat to integrity, definitely. And then is masquerading. Masquerading is simple, is a second word for impersonation. So that is it is an attack to the integrity. Means herein also we basically modifying the data in some way. Then it is replaying. Replaying is also a type of an attack to the integrity, in which the same message which was exchanged previously will be used by the attacker for the purpose of for a purpose of harming the system. So that is replaying. Replaying the request which is not the legitimate basically request, which it is a request which is made earlier, and it is replayed by the attacker in some way. Then repudiation, as it is a common attack, which is wherein basically the sender and receiver both can be considered as attacker here, in which the sender may later on deny that I've sent the message. Means definitely it is a type of attack. Then at the same time, it can also be the receiver of the data of the packet, which can later on said that I have not received the message which was sent by the server by the sender. So this is denial of basically denial of a message which was sent earlier either by the client or by the server. So it is any one of the two, that is client or the server, which can later deny that such kind of message was exchanged previously. So definitely the solution to that is that we need a system in which we're able to impose non-repudiation. But these are the attacks which are important to take to be taken care of. So then moving ahead, these are the threats. Then moving ahead, so this talks about various cryptographic goals. So herein it included one more pillar of security, which is authentication, which was not covered before. So we have confidentiality. So now we, considering the cryptographic goal, any cryptographic system want to achieve confidentiality. Then data integrity, we have already discussed confidentiality, data integrity. Then authentication is another aspect. Then there is non-repudiation, which we have already discussed. So achieving confidentiality can be done with the help of cryptographic algorithms. So we have symmetric key cryptographic algorithm, we have public cryptographic algorithms. So as you have, if some of you have already gone through the literature, then there is the use of key for the purpose of applying encryption decryption. So if the key happens to be same for encryption and decryption, it is that type of, which is called a symmetric key cryptography. Whereas if it is a case of two different keys being used for encryption decryption, then it is definitely a case of asymmetric key cryptography, which is also called as public cryptography. So then in this slide, it has listed some block ciphers, stream ciphers also. So we'll be talking about some traditional ciphers in the subsequent slides. So because that is any literature about information security is incomplete without the use of those traditional ciphers. So this is basically means by for the purpose of achieving confidentiality, we can apply either of the two types of cryptography. One is symmetric key cryptography, another one is asymmetric key cryptography. In symmetric key cryptography, we'll make use of a same key. And all the traditional ciphers we studied, they all were symmetric in nature, whether that is, additive cipher or that is multiplicative cipher. Means I'm talking about, Caesar ciphers followed by Vernam cipher, Hill ciphers. They all are basically symmetric ciphers, which make use of the same key for the purpose of encryption, decryption. And later on, we comes up with an idea of asymmetric cryptography. So then second goal we have already discussed is data integrity, wherein the purpose is to achieve, safeguarding the modification of data. So, and very good example for achieving that, for ensuring integrity of data is MAC, message authentication codes. So I think you all must have heard, if not studied these MACs. We have various algorithms which talks about, generating MACs. Then we have authentication as the third goal, cryptographic goal, wherein the purpose here is to authenticate the users of the confidential information, whether that is sender or the receiver. In some of the cases, the authentication is required as an important parameter of the communication. So for that purpose, we need authentication of either side of, means either it can be user, which is means either it can be a client which needs to be authenticated. In some cases, it may be the server which need to be authenticated. So, but for achieving that, we have various algorithms, and MAC is also providing that facility for authentication. And distal signature is definitely another one for providing the services of message authentication. Then non-repudiation is basically proving later on that somebody who is denying that I've sent the message. So there is a way out for that distal signature if it is sent by any of the server, any of the user with distal signature on that particular document. So in that case, you cannot deny later on that I've sent that message. So the non-repudiation. There are some other techniques also, but only few are listed here. So these are four important security cryptographic goals which need to be taken care of in any of the system which is asking for security. Yes, I already told you that there are some of the traditional ciphers which need to be studied in any of the information security, in any of the lectures of this information security. So so then, yeah, this is that classification. So in this classification, we see that there are two types of traditional ciphers which are a part of literature. They are substitution cipher, or it can be transposition cipher. Substitution ciphers are the ciphers which requires that the input plain text need to be substituted with some other characters or symbols. So and then furthermore, these substitution ciphers can be broadly classified as monoalphabetic cipher and polyalphabetic cipher. So in monoalphabetic cipher, means every single alphabet of the input plain text, they are being transformed to some other single character, but this mapping is always fixed. Whereas in the case of polyalphabetic ciphers, the plain text characters they are being replaced by a single character, but the single character which is acting as a replacement is not fixed. So in simple words, we can say that basically we have this there will be, if you talk about the mapping of the input plain text and the cipher text, then the mapping is 1-to-1 in the case of monoalphabetic ciphers, whereas the mapping will be 1-to-many in the case of polyalphabetic ciphers. So means there are various, means at one point in polyalphabetic cipher, means suppose we're talking about any of the plain text where where the English alphabet is used. Means there is no other type of alphabet. Suppose for the sake of simplicity, we can take that example, that we have English alphabets as an input plain text. So in that case, at some point in time, the letter A is replaced by C maybe, and some at some other instant, the A might be replaced by some other letter, say F. So that is the point. That's an example of polyalphabetic cipher. So wherein every character is replaced by different characters at different times. So this is polyalphabetic, and otherwise it is monoalphabetic ciphers. So the other classification of traditional cipher is that if it is not substitution, then it might be a transposition cipher, in which the position of the letters in the plain text is basically changed. So this is transposing the input plain text characters to generate cipher text. So that is the concept of traditional ciphers. Okay, so this is an example of traditional cipher, in which you can see that we have the plain text on the left side, and we have the decryption algorithm, that we are decrypting the plain text back at the receiver's end. So LS is considered to the sender. So in that case, we have a plain text and we have an encryption algorithm. So encryption algorithm, and you can see that there is a same key, that is a symmetric key, being used by the sender and receiver of the message for the purpose of encryption and decryption. So at the sender's end, the LS, that is sender, will be applying the encryption algorithm on the plain text to generate the cipher text with the help of the shared secret key. Then the encrypted data will be sent to the receiver, and the receiver will be applying the decryption algorithm to retrieve back the plain text. So this is the concept of this. This is a symmetric key cryptographic concept. So in a substitution cipher is a matter of encrypting by units. Yes, we have discussed that. So this is the definition of substitution ciphers. So, and more precisely, a few of the monoalphabetic ciphers are listed here. So a monoalphabetic cipher is a substitution cipher in which, for a given key, the cipher alphabet for each plain alphabet is fixed throughout the encryption process. Yes. So we have already discussed that the mapping of the input plain text and the output, that is cipher text, will be one-to-one. They will always be, like for example, A is encrypted as D. For any number of occurrences in that plain text, A will always be converted into D, encrypted to D. So the examples are additive ciphers, multiplicative cipher, affine cipher, then you have monoalphabetic Caesar cipher. These are few examples of monoalphabetic ciphers. So okay, so let's have a just if you are aware of, if you are computer science people, then you will be aware of, means you will be understanding what I was speaking of. Like, because in additive ciphers, what happens is basically that we have the sender and receivers. In all cases, we have the two parties communicating. We have the sender and we have the receiver. And for the sake of understanding these four ciphers, we assume that the data will be exchanged in English alphabets only. So that is, by that means, I can say that all the letters that are a part of input plain text will be from A to Z only English alphabets, for example. So in that case, what happens in additive ciphers, there is a use of the additive inverses. So in additive inverse, what happens is, like, every integer, that every integer has got its inverse. So similarly, we have inverses, the concept of additive inverse in modulus arithmetic also. So modulus arithmetic plays a very important role in cryptography. So in modular arithmetic, what happens is we apply the mod operation. So in additive ciphers, as the name says, additive, so it makes use of additive inverses. Like, if you assume that if we have an alphabet of 10 characters, for example, so in 10 characters, suppose they are being represented by, suppose, integer numbers ranging from 0 to 9, for example. So in that case, for any number in that list of 0 to 9, we always have an additive inverse. And additive inverse is for example, we have, like, for one, the additive inverse will be 1. inverse will be 9, because it will be 1 plus 9 when we apply mod operation on this, because the total number of alphabets suppose is 10. So it is 1 a, suppose a is 1, we are finding here the additive inverse of a, that is 1 here. So 1 plus 9 becomes 10, and 10 mod 10, because the modulus used here is 10. Modulus is total number of alphabets, total number of letters in that alphabet. So if it is English alphabets, then the value of modulus will be 26. And if it is, as an example that as I've taken, suppose we have in the input plain text, we have the numbers which are ranging from 0 to 9, means we have only 10 numbers in the alphabet. So in that case, they will be represented by 0 to 9. Or if you are considering English alphabets, so we have the numbers, we have the alphabets A to Z, which are given in integer value from 0 to 25. Fine. So suppose we are asking for what basically is the additive inverse for 0, then it will be 0. It will be 0 plus 0 modulus of 26. Means the answer should always be 0. Means when we apply the modulus operation using the modulus value 26, the result of a plus b mod n should be 0. So that is the condition of finding out the additive inverses. The point here is, what we do in additive inverse is, additive cipher is, we represent, like suppose we need to encrypt a, and a suppose is represented by say 0. So in that case, and if it is an example of a symmetric key, then same key will be used as the sender's end and receiver's end. So in that case, what need to be done is, either we can add the key value at the sender's end, and we can subtract the that key at the receiver's end to decrypt back. So would you discuss ECC if possible? That is not a part, Sanjay. This is not a part. We have not included this in this in this slideshow. Am I audible, Sanjay? Okay. So this is a basic additive cipher. So we'll be making use of additive inverses in this case. Similarly, on similar grounds, you have multiplicative cipher, wherein multiplicative inverses comes into picture, and we have, because not every number has got its multiplicative inverse in integers. So in this case also, in modulus arithmetic also, so we'll have only few keys which are eligible for being a key in the process of encryption. Whereas in additive ciphers, you can have any key possible out of the alphabets. Then affine cipher is the combination of the two, that is additive cipher and multiplicative cipher. So we can apply them in any order. You can first apply, means add senders, and if you apply additive cipher first, followed by multiplicative cipher, then at receivers end you will be applying multiplicative cipher, decryption of multiple cipher first, then the decryption of additive cipher. So I think you people are understanding why I'm speaking out. If you can respond to my so I'm speaking what, like, you are able to understand all these algorithm. If you can write, yes, we are understanding, either you can speak it out or you can write on this message box. Is the concept clear? Am I audible?
Yes, sir.
Okay. Fine. Thank you. So in this list of monoalphabetic ciphers, we have tried to finish up additive cipher, multiplicative ciphers, and then the combination of the two, which is affine cipher. Then we have monoalphabetic Caesar cipher, in which basically every character is assigned a substitute, a given substitute. Means basically how it is different from the earlier one is that here in this case, means there is no fixed key. There's no fixed key, but the key here is already, since we have assigned character for every character of English alphabet. So this is monoalphabetic cipher. So by that mean, we can say that A can have 25 possible replacements. So it is basically what is the key domain in this case is we have the highest key domain in the case of monoalphabetic Caesar cipher, which is 25 factorial, because we can replace A with the remaining 25 alphabets. So definitely, because so if we are talking about the key domain here, and key domain plays a key role in the strength, in checking out the strength of any of the algorithm. So means the more the key domain is, the more powerful this algorithm basically is. So, and the various examples are AutoKey cipher, Playfair cipher, Vignier cipher, Hill cipher. So if okay, this is given here. So, okay, AutoKey cipher is not listed out here. It's not explained here. So although in AutoKey cipher, what happens is both sender and receiver, they agree upon this AutoKey cipher, in which the key generated at the sender's end will be the first character. Means if the first character is A, then corresponding to that, the A will be considered as means the integer number corresponding to A will be considered as the first sub key, because it will generate the complete stream of sub keys in AutoKey cipher. So the first letter will be the plain text, means the first sub key will be the first plain text letter, followed by means all the trailing numbers will be the means the first letter is agreed upon, then we have all the plain text characters will form the remaining sub keys. So this is how the stream of sub keys will form the actual key, and that key will be means then we can apply the additive cipher to that, and we can generate a ciphertext out of that. Then second, so in this case it's quite clear that for every character you will be getting different replacements. So definitely it is a clear-cut example of a polyalphabetic cipher, this AutoKey cipher. Then this is a Playfair cipher. In the Playfair cipher, basically there is the use of a 5x5 grid. So in that 5x5 grids, we have 25 alphabets. It is said in the literature that I and J usually do not come subsequently. So that means the frequency of getting I and J together is quite less. So in that case, they are kept in the single cell. So this is how the 26 alphabets are kept in 25 cells of 5x5 grid. And there is there is a policy, means how will be forming the ciphertext here is that basically there are three possibilities. That suppose we have a plain text with us, so we'll form, first of all, we'll form pair of two characters. So for that to happen, we definitely requires the number of plain text characters should be even, and if it is not even, we are going to make it even by adding a bogus character to it. Then every pair of characters will be replaced by two characters, and that too by looking at this 5x5 matrix. So in 5x5 matrix, there are three possibilities, that the two characters in the pair, either they belong to the same row of the table, or they belong to the same column of the table, or the third possibility is they neither belong to the same column, nor they belong to the same row. So in that case, there is a replacement policy. Means if they belong to the same row, then they will be replaced by the next character in the same row, and this operation is a circular operation. And similarly, if they belong to the same column, then they will be replaced by next character in the same column. Whereas if they do not belong to the same row or column, then definitely will be replacing the character with the intersecting character in the same row. So this is how the Playfair cipher works, and it is definitely a case of a block cipher in which the block size is 2. Block size is 2 means that two characters are replaced simultaneously, and the key here is the 5x5 matrix. So you can say that if we have 25 possible cells in the matrix which is acting as a key domain in this case is also 25 factorial. Then is a Vignier cipher. In the Vignier cipher, basically it looks quite in terms of functionality, it looks quite similar to AutoKey cipher, but it is different, because in this case also we need to generate the complete key by repeating the agreed upon sub key. First of all, the sender and receiver, they agree upon a sub key. Like in this example, it is listed in here that let's assume the key is point. So corresponding to point, if we are being assigning integer numbers to the English alphabets, then for P it is 15 number, and for O it is 14 number, for I it is 8, for N it is 13, and for T it is 19. So these are the integer numbers which are assigned to the English alphabets, and of these alphabets P, O, I, N, T is taken as a subkey. Then this subkey is repeated to form the complete key, and that depends upon the number of characters in the plain text. So this is how the key is generated, and then we'll apply the series of additive cipher to generate the corresponding ciphertext. So this is how beginner cipher work. Okay, so till now, all the ciphers that we studied, they are all substitution ciphers. Then comes the discussion of transposition cipher. It is another type of cipher where the order of alphabets is the plain text is rearranged to create a ciphertext. And if you have studied that before, then there are basic techniques of transposition ciphers. One of them is rail fence. Yes, it is listed here. So rail fence cipher, wherein the plain text character are written in two different columns and two different rows, and they are read zigzag way. So basically, that is a rail fence method in which what we are doing is we are only transposing the input plain text characters to find the ciphertext. And another is a better technique, which is a columnar technique. So then in columnar technique, basically we have one version wherein we are not making use of the key. Then another type of columnar technique comes up with a key, which is called as key transposition cipher. And then the two techniques can be combined, means the keyless transposition cipher and the key transposition cipher can be combined to form a combined approach. So let's see what happens here. Yes, this is an example of a combined approach. So as we can see here that on the left side, you will see that the plain text is enemy attack tonight. Then we have written Z finally. So basically, Z is added as a bogus character here. So what happens in the case of in the case of keyless cipher is that we write all the plain text characters row by row by first fixing out the number of columns that is fixed between the sender and the receiver. So in this case, Alice and Bob will agree upon that the number of columns, you will see on the left side that we have taken this pointer. You'll see here that on the left side, you will see that this is the input plain text. So in this plain text, both sender and the receiver, means the Alice and Bob, they agreed upon that they should make use of 5 columns. So it uses 5 columns, and it has written this, then it will count that the number of plain text characters will definitely be a multiple of 5. And if it is not a multiple of 5, then it has to make it a multiple of 5 by adding that much number of bogus characters. So it has to add 1 to make it a complete multiple of 5. So this is how Z is added to the end of the plain text. Then it will write all the plain text characters row by row by considering in these 5 columns. So it is enemy, attack, tonight, then Z. This is how the plain text characters will be written. So, the number of rows is fixed, number of columns is fixed. So this is definitely we are not making use of. So this is then it will be the concept of columnar is then it will be sending out these rearranged plain text characters column by column. It will sending it column by column. This is keyless cipher. So this is this is a slide wherein we are making use of a combined approach in which first of all the keyless cipher is applied to rearrange the plain text characters in this format, followed by the use of keyed component of the transposition cipher, wherein the key is used. On the top of the slide, you will see that this is a key here. This is a key here. So in this, the key is basically means that all the plain text characters, they will be rearranged, like 3 is replaced by 1, 1 will be replaced by 2, 4 will be replaced by 3, 5 will be replaced by 4, and 2 will be replaced by 5. And the decryption is just opposite of that. So this is encryption. This is decryption. So third means, because we have considered the size of means the block as 5, so so it is a 5-bit key in which, and this is basically, this key will be helping out in transposing the plain text characters into different locations. Means third characters in the position of third will be replaced by first character will be replaced by 2, and so on. So this act like a key. So in this was a part of keyed component this transposition cipher. So this approach is applied in this combined approach method, and this key, rather than replacing it replacing the characters, it will be replacing the complete column out here. Means the first column will become second column, like here the first column becomes second column, then the second column will become fifth column, like see here, third column will become first column, third will become first column. This is how you will be rearranging the columns as per the key. This is during encryption, and this is finally that you got after applying this key, and then it will be read column by column. So first this column will be read, then this column will be read, then this column will be read, this will be read, and finally this column will, and this is sent to the receiver, and the reverse process of that will be used in the decryption. So this is a combined approach wherein we're making use of keyed and keyless component of transposition ciphers. So you can see that we are not replacing, we are not substituting here the letters, we are just changing position of the input plain text to generate ciphertext, and similarly just an invertible algorithm is applied at the decryption end to retrieve back the plain text. This is how it is taking place. Okay, so once we are done with this this plain traditional ciphers, with either it is a case of substitution cipher or a transposition cipher, then comes your modern ciphers. So modern ciphers basically are considered very important because they are made too complex, that they have the algorithm is developed in such a way that they make use of the strengths of the traditional ciphers and other concepts that added more confusion, diffusion in the mind of the attacker. So they are made quite complex, and definitely they make use of the concepts of traditional ciphers also as a part of their own algorithms. So you will see that in DES also, you will see that there are various components which are used, AES, DES, in all these symmetric cryptographic algorithms. You will see that there is a use of these traditional cipher components. They're using them as various components. So I think we have included in this slide. So yes, so this is the concept of the modern cipher, that what we do is usually make use of block cipher as a part of modern ciphers. That means we'll be encrypting the plain text in a block of n bits. So on the left you will see that we have a complete n bit plain text. Basically you have a plain text of any size, then that plain text will be divided into blocks of n bit each, and if the block size is not a multiple of n bits, then we'll be adding some padding bits to that to make it a complete n bit block. Then that n bit block will be applied on with the encryption algorithm, and which will be generating a n bit ciphertext, and then at the receiver's end the ciphertext will be converted back to the plain text with the use of decryption algorithm. So in this basically it makes use of this slide basically shows that it is a symmetric cryptography which make use of the same key for encryption and decryption. Okay, then any of the modern block cipher that you study, whether that is encryption, advanced encryption standard, or it is data encryption standard, whether it is DES or AES, so means all of them, they make use of the various components, as I already discussed. That number of components, it look quite similar, that we have already studied as a part of transposition cipher. We'll see that on the slide we have few transposition ciphers, few components which are transposition, which is applying transposition only. You have three types: straight permutation, compression permutation, expansion permutation. So from the diagram itself, it is quite clear that in straight permutations, we are transposing the input plain text characters to the cipher text characters. And whereas in the case of compression and expansion, basically the number of input and output characters or bits is not same. So basically, I mean to say here is that there are some component in transposition also, in using transposition ciphers also, wherein which make use of non-invertible components. So out of these three, straight, compression, and expansion permutation methods, only the straight permutation method is the one which is invertible, whereas compression and expansion, they are non-invertible components. Non-invertible clearly means that we are not able to use that in decryption algorithm because they are not going to retrieve back the plain text. So these are non-invertible components. You will see that the significance of non-invertible components also when we study those modern block ciphers. So this is transposition ciphers. Then there are some some other components also which are used in these modern block ciphers, and they are, see that we have substitution. We have already discussed that. We have substitution cipher here. Then we have XOR operation, which is a very important component of modern ciphers because it is invertible in nature, and whenever you apply or this XOR operation, this is always used in a situation which requires the data to be retrieved back in. So this is invertible. That's why this is the property of XOR operation. Then you have a shift operation. It is a circular shift wherein you can apply the right shift, and at decryption you will apply the left shift or vice versa. So this is definitely an invertible component. So we have XOR operation, shift operation. These are invertible components. Then we have swap operation, which is also considered. It is similar to the split and combine operation. So basically, what you do in swap is you find the number of number of bits in the block is, if that is even, then we can apply this swap operation. So we can swap the left half with the right half, and so and we can just you use the reverse of this at the decryption, and so that we can retrieve back the original plain text. So this is definitely invertible. Split and combine looks quite similar to this. So we split at the maybe at the receiver's end, at the sender's end, and we can combine at the receiver's end. So this is again. So these are various components which are used in the algorithm of modern block ciphers. So yes, this is another classification which is made that then there are two important components. Diffusion confusion means which will add which make it more complex to break out diffusion confusion. These are properties basically, and on the basis of whether we are making use of invertible, non-invertible components in this algorithm. So we have classified these ciphers into feastal ciphers, non-feastal ciphers, feastal ciphers and ciphers which make use of both type of components in their algorithm, like A and like DES. DES is a feastal cipher which make use of both invertible and non-invertible components in its algorithm. Whereas non-feastal cipher is AES, because AES uses only invertible components. So this is that classification. Okay, this is the structure of DES. Now we're discussing few ciphers here. So this is a structure of DES, wherein you will see on left side that total there are 16 rounds. It is listed out here. Wait. A total 16 rounds in DES. I will be covering it up fast. So in this case, what is important in DES is that it is a symmetric cipher, one thing. That means same key is used for encryption, decryption. Then the number of bits in the block means the block size of DES is 64 bit. You will see on the top that we are processing these 64 bits. So we'll be applying various operations on those 64 bits because that is the size of the block in DES. So it is a block cipher, it is a symmetric cipher, and the size of the key used in this DES is 56 bits. So then there are total number of 16 rounds. So we are adding each round is similar, but every round has got a different key. Then we are running out these rounds, 16 rounds, to adding more complexity to the system. So you'll see that we have what we have done here is that the block is divided into two halves, two equal halves, left half and the right half, each of 32 bits, and it is processed in this way that each round is comprising of two steps primarily. One is a mixture and another one is the swapper. Swapper is just swapping out the left half with the right half, means the output of this portion will be made as the right half, and the left half was the one which was earlier the right half, so it becomes the left half. So this is done at each round. Then each round will be having a new pair of key, a new key basically of 56 bits, which is applied here. So you will see further. Yes, so this is how the DS look like, that we have a 64-bit plain text. Then we applied an initial permutation, final permutation, where it is nothing but a simple straight permutation, which we have already discussed in the previous slide. Then in between you have 16 rounds, and those 16 rounds, in each round you'll be getting 48 bits key from this round key generator. So this round key generator will be generating basically the input to it is a 56 bits, which is an agreed upon key between the sender and the receiver. Then in each round, the key generator will generate a 48-bit key, which will go to each round. So this is the structure of DES. See that there are four components here of this is function. This is the function. We have elaborated this function because in every mixture you have this function and this XOR operation. So this is very important. This function itself comprises of four operations. Because in this you will see that there are the right half of the plain text, means the 32 bits of the right half will be input to this function, and the other input to this function is the key. So this is elaborated here. So we have the right half 32 bits which is fed into expansion P box to make it a 48 bits. How we are going to make it 48 bits is the few of the inputs bits are repeated in the output bits. So that is how we're going to expand the number of bits from 32 to 48 bits. Once it is made 48 bits, then this 48 bits will be XORed with the 48 bits of the key, which is sent to this round by the key generator. And then after that, you will get an output of 48 bits, which is divided into 8 sub-blocks of 6 bits each. And furthermore, those 6 bits will be converted back into 4 bits, and ultimately we are left out with 8 crossed 4, that is 32 bits as an output. So this is S boxes which are applied here. These are substitution boxes, and by looking at these operations, it is quite clear that both expansion P box here and this S box here, they both are non-invertible components because the number of input output bits is not the same. So after that, those 32 bits of the output of the S boxes will be fed into straight P box. We'll be applying the straight P box, which is definitely invertible, and we're getting out 32 bits as an output. So this is then after that, this is the 32-bit output that we get out of this function, and this is fed into this mixture, and these two, the left half and the 32 bits of this output of the function, will be applied on with this XOR operation, and the output will become, ultimately it becomes the right half. So this is how each round will behave and it will act upon. So then, okay, this is also discussed here. Now this is the generation of key, which I already talked about, that initially we have 56 bits, then those 56 bits will be fed into key generator algorithm. What it will be doing is it will be applying various components. We have shift operations here, we have splitting operations, we have combining operations. So we have few operations which are applied on those 56 bits, and it will generate 16 keys, and each key will be of 48 bits, and all these keys are different keys. So this is how means we'll be generating out keys for every round, 16 rounds, 16 keys. That was about the DES function, which is considered a symmetric cryptographic algorithm. So followed by Diffie-Hellman key exchange algorithm. This will be wrapping out it fast. So basically, it is an algorithm which is used for the safe exchange of shared secret key between sender and receiver, because in symmetric cryptography we require the require the sender and receiver both having a same key for the purpose of encryption decryption. So we're doing it fast. So this is the algorithm, key exchange algorithm. Both Alice and Bob, they agree upon two large prime numbers n and g, and it will be generating, means both the sender will be generating, for example, because the two number n and g are known. So these are two large prime numbers. So what LS will do is it will generate another large random number x, and it will calculate the value of a. Capital A will become g raised to power x more than n. Then LS will send the value of a to b to the Bob. Then Bob individually have its own value of the random number y, which it will generate at its own end, and it will calculate the value of b at its end, which is g raised to the power y m mod n. Fine. So then it will send it to Alice, and furthermore the keys will be generated, k1 at the a and k2 at b. It will be b raised to power x, because now the sender a has got the value of b, and similarly b has got the value of a. So this is how they will be calculating k1 and k2, and definitely you will see that we are fortunate enough to find that the two values are exactly the same. K1 is equals to. This is how the shared secret key is being exchanged between sender and receiver using Diffie-Hellman key exchange algorithm. And definitely there is, or this is an example given. See that you can check it out on your own also, that if Alice and Bob, suppose they agree upon these two large prime numbers, 23 and 9. We are taking it small although. So these are two prime numbers, 23 and 9. 9 is not a prime number here. This is a wrong example. So if you're taking it, if definitely they are to be two prime numbers. So 9 is not a prime number. So then it will calculate the value of a and b. Then they will exchange the values of a and b, and ultimately they will be generating two numbers, k1 and k2. We are taking it prime because it will be difficult to crack it out. So, and that too are very large prime numbers, which is very difficult to final factorize. So this is a simple example of a Diffie-Hellman key exchange algorithm, means how they will be exchanging the shared secret key. But this too suffers from a drawback, that is these are the applications. So with the man in the middle attack, there is a problem with Diffie-Hellman key exchange algorithm. This is an example which shows that the Diffie-Hellman key exchange algorithm suffers from this problem. So let's consider, like suppose Alice and Bob are the two parties in communication, and suppose Eva is the one who is the attacker, who is able to have an access of the keys of basically the to the prime numbers, because they are made public. N and G are public basically. They means Alice and Bob, they will be exchanging two numbers public on an insecure channel. So definitely attacker can have a access of that. So attacker has also the two numbers n and g with it, the two large prime numbers. Then Alice suppose generated random numbers, for example 3, and Bob generated a random number, say this is just for the sake of example that I'm taking these two small numbers. So although they are large numbers, and so suppose Bob take it as 9, then Alice will calculate the value of a, that is g raised to the power x mod of n, and it comes out with a value of 2. Similarly, Bob will calculate the value of b, and it comes up with a value of 8 here. Now, so what Alice will do next is it will send its value to Bob, but intermediately this Eva will intercept this and will keep this value of a with it and pass it on the value of a which it has calculated, because it has also generated a random number here, and the random number suppose here is taken it as 8 here for calculating value of a, and the random number for calculating the value of b, suppose it takes as 6. So this is how the attacker will generate its own value of a and b. A here is 9 and b here is 4. Now because now Alice has sent the value of a to Bob, but it was intercepted in between, and Eva, instead of sending the value that Alice has sent, it will send its own value of a to b or to Bob. So Bob will have the value 9, which was not the actual value of a which Alice had generated. So now the Bob is having an excess of value of a, which is 9, and b which it has calculated. Similarly, Alice will have the value of A, which it has calculated, and the value of B, which it receives from the attacker rather than from the actual sender, that was Bob. So then ultimately, all that means we can now make up the point that whatever is being sent by Alice will be quite easily decrypted by this attacker, and now it can, because the actual data will not reach to the Bob. So this is how this is called as man in the middle attack. So this was a problem with symmetric cryptography. So because of that, because of the problem of the sharing the secret key, which is a problem in asymmetric cryptography, then asymmetric cryptography comes into existence, and the very important asymmetric cryptographic algorithm is RSA, which is named by Ravis, Sharma, and Edelman. So, and this is again based upon two large prime numbers. So, okay, this is also the algorithm which chooses two large prime numbers P and Q. We're just making it fast. Basically, this is RSA. RSA basically is an asymmetric cryptographic algorithm. And for those who are interested in studying it, if you don't have an idea of RSA, then it is quite a simple algorithm that I have listed out here in simple words. So two large prime numbers P and Q, it will calculate the product of P and Q, then it will find out and because here RSA is an example of asymmetric cryptography, so it has to generate, means all the users has to generate their own public and private keys, and private keys are known to the users only, and the public key can be made available to other users also. So it will generate, every user will generate its own pair of keys for any communication to be possible using RSA. So this is the use of two large prime numbers, and it is the basis of this is that the product of the two large prime numbers is very difficult to crack out, because we're talking about large prime numbers of nearly 100 digits. So it is very difficult to crack that. So this is the example will also we'll find here. This is the algorithm. So what is done in RSA basically is that it is the receiver of the message, means the actual receiver which want to receive something from A will be generating its own public private key, and will be sending the product of the two number n, which it is actual the product of the two large prime numbers P and Q, n, and its own public key to the sender. Then what the sender will do is, because it has got the actual plain text, so the actual plain text will be encrypted with the public key of the receiver, and it will be sent to the receiver. Then the receiver will be decrypting the cipher text that it receives from the sender with its own private key. So this is how RSA works. So this is an example. Let's select the two prime numbers. Suppose they are 17 and 11 taken. Then it computes the value of n as the product of PQ. Then it will calculate. This is the way to calculate the encryption key. The encryption key is chosen in this way, such that it should not have the same factors as the factors of P minus 1, Q minus 1. This is how it will be chosen. So suppose the value chosen is 7 here. So it will be then this we will use to find out the value of the decryption key. So decryption key for the encryption key 7, the decryption key comes out to be 23. So this is the equation for that. So then so the public private keys comes out to be the encryption key is 7 here, and a decryption key is 23 here. So this is how public private keys are generated by each user. Means if we have n users in a system, then in the case of RSA, then every number of users will have its own pair of keys. So if n users are there, and if n user want to communicate using RSA, total number of keys comes out to be 2 into n. So this is how encryption take place, decryption take place. This is quite simple. Okay, then talking about so this slide talks about message authentication code. So because now we are done with one symmetric cryptography, that was DES, and another asymmetric cryptography, that was RSA. But both of them, the main emphasis in both algorithm is to secure the confidential information. So the purpose there is to ensure confidentiality. So now when comes the the concept of MAC, which is message authentication code, the purpose here is definitely to safeguard the integrity of the data. So basically, what is done in this, in this MAC basically is that we have got the data with us. It will be generating a MAC out of that data, and then that MAC along with the data will be sent to the receiver, and receiver will again calculate its own MAC, and if it found to the same MAC, means if the MAC matches, then it is okay, otherwise data will be rejected. This is how to ensure integrity. So in Mac, basically, there's a slight difference between, if you have heard about message digest algorithms, which is MD5, which is the most popular one, or SHA. So these are, these are the algorithms which are used to generate message digest. Both of them, Mac also and MD5 also, they are used for the purpose of ensuring integrity. But in Mac, you will see that there is a concept of shared secret key. Shared secret key. Shared secret key will be basically used to add encryption component into it, but it is again different from normal cryptographic algorithm, because at senders and receivers end, basically we are applying only encryption and no decryption. So this is how the message digest algorithm is different from the basic cryptographic algorithms. Another is a digital signature scheme. Basically, what happens in this digital signature is, you might be aware of this, that it is again asymmetric cryptography. So in this what happens is, in the encryption is taking place with the private key of the sender. This is how it is different from RSA type or other crypto asymmetric algorithm. So because in this case, the purpose is clearly not to achieve confidentiality, but to achieve authentication, non-repudiation, integrity. So whatever is to be sent by the sender, it will generate, it will basically it will encrypt the plain text with its own private key. The purpose here is that the encrypted text will be sent to the receiver, and because the public key of the sender is known to the receiver, so it will be decrypting that clearly. So it is not possible to decrypt the encrypted text with any other key but the public key of the sender. So that's why we are ensuring authentication, non-repudiation, and integrity here. And clearly not confidentiality, because the public key of the sender is known to everyone. So everyone is gonna decrypt the message which was sent by the sender. Fine. So definitely, if we are to in similar cases, if definitely we have a confidential information and we want to ensure confidentiality also, then we have to use some of the other applications which ensures confidentiality, because this signature is going to ensure authentication, non-repudiation, and integrity only. This is MD5, which is, again, I told you that it is a message digest algorithm which is used for the purpose of ensuring integrity of the data. This is, if you are interested, then this is comprising of various steps, in which the size of the block is 512 bits, means we'll be processing the input plain text in the block of 512 bits, and the output MD5 generates an output of 128 bits. So 128 bits is the final output that we get out of the MD5 algorithm, and that is basically considered as of fixed size, means whatever is the size of the input plain text, it will always generate an output of 128 bits. So there are various steps involved in this MD5 algorithm, means whatever is the size of the plain text, first of all, we need to convert it into blocks of 512 bits. Then furthermore, the 512 bits, this is the concept how you will be adding out the padding bits to it, which will see that it is a typical case of adding bits. So because in every case you have to add some padding bits ranging from numbers 0 to 512 bits. Then a component of the length of the message is added upon. Then it make use of 4 registers, ABCD registers, which collectively form a 128-bit value, and this is the final value. Basically, although they are the 4 different registers, but they are taken together to form a value of 32 cross 4 bits, that is 128 bits, and it has got the initial values are listed on the screen. So these are the few values of A, B, C, D registers, means these registers are initialized to these values. And these are the 4 processes which are, because it comprises of 4 rounds. Each round means this MD5 algorithm has 4 rounds. Each round will have its own function. And you will see then these are basic logical functions. So we'll apply these functions on X, Y, and Z, and you will get out the value, and which will be fed into this process. You will see it is not listed out here. So this is the use of MD5 algorithm for the purpose of for ensuring integrity. So then there are a few case studies which are listed, which are added on here. So I will be sharing this screen with you. So a few a few case studies are included here in these slides. So these are few there's nowadays we're talking about different types of algorithms. We'll be talking about different type of quantum computing and all, which are used in encryption and all. So this is all from my side. This is covering up basic topics of information security. So if you have any questions related to these slides, you can ask me. Are you people available?
So dear participants, if you are having any query, questions, so please you can ask now. Anyone?
So I've basically tried to cover a few topics which are important with respect to information security topics. Means either it is a subject of BTech or MTech. So I've tried to cover those topics.
So definitely, sir, these are very important actually. If we are, please share attendance link. Okay, that we are going to share, and definitely the basic concepts are very important to understand whatever building is over there. The basics, basically understanding the basics is necessary. Even we have some of people have discussed about the blockchain technology and the other technology security over the clouds, but it is necessary somewhere these concepts are used. So they are very important. And I'm also seen that the your session is very informative and nicely you have explained, sir. So thank you very much for being with us this session. uh, thank you very much, sir.
Thank you, Dr. Krishna. Thank you for this.
Thank you, sir.
Okay. Thank you all.
So dear participants, in the next session that is going to start at 3 o'clock, we are having one professor from IIT Roorkee, Professor Manoj Mishra. Okay, so kindly join on the time. This is my personal request to all of you. Okay. Yeah, definitely we have actually requested to the experts, different experts. If they share the PPT to us, then definitely we'll share the PPT to all of the participants. So thank you very much all of you for attending the session.